Hello everyone, my name is João Paulo Bezerra and I am a PhD candidate at Telecom Paris from Institut Polytechnique de Paris. I'm going to talk about the paper Relaxed Reliable Broadcast for Decentralized Trust, which is a joint work with Professor Petr Kuznetsov, also from Telecom Paris, and Alice Koroleva from ITMO University. Throughout this presentation, I'll be exploring the following subjects: the motivation for this work, I will be revisiting the concepts of classical quorum systems and Byzantine reliable broadcast, and then introduce the decentralized trust model and the relaxed version of the broadcast protocol for this model. I'll also introduce a graph representation of trust used to show a lower bound on the consistency parameter of the broadcast primitive, and a high-level description of the algorithm, which shows the bound to be tight. Finally, I'll be discussing future work. Recently, some decentralized blockchain applications, such as Ripple and Stellar, have popularized an approach to quorum systems where each participant chooses whom to trust in the network. This approach appears to be more suitable for open and large quorum-based protocols. For instance, it allows the participants to wait for replies from a small subset of other processes in order to complete an operation. But this model also comes with its vulnerabilities. Some participants might end up trusting the wrong people. We can look at the example presented in this slide. So here, if Carl is a Byzantine participant, then Alice might end up accepting both operations since Carl is the only system member she trusts. Since it might be difficult to guarantee global consistency, we ask the question of what is the strongest class of protocol that can be implemented in the decentralized model. To help understand the answer, we consider the broadcast problem and present a relaxed definition of consistency that is more suitable for this decentralized model. But first, let's recall the concept of quorum systems and the definition of the classical reliable broadcast. So a quorum is a subset of participants that intuitively can act on behalf of the whole system. A quorum system is then a collection of quorums whose main purpose is to guarantee availability and consistency, even in the presence of failures. In the classical approach for quorum systems, every process uses the same collection of quorums, such that every two quorum intersect in the correct process, and at least one of the quorums is composed entirely of correct processes. If we assume Byzantine failures, that is, faulty processes can behave arbitrarily, one of the well-known results is that a system cannot tolerate more than one-third of Byzantine processes. In the following simplified example, we illustrate the execution of a quorum-based protocol. Alice and Bob consult a quorum before executing an operation. Since their quorums are composed of 3 members, even if, for example, Carl becomes Byzantine, the system might still maintain consistency because Daniel is in the intersection and Daniel is correct. So before talking about the reliable broadcast problem, in our system model, we are assuming that the system is static, that is, the set of participants is fixed. We also assume a fully connected network, but with asynchronous communication channels, and that digital signatures are available. In the reliable Byzantine broadcast problem, a single process invokes operation broadcast V, where V is a message value, and processes output deliver V, such that if a correct process delivers a value, then every correct process eventually delivers a value. Moreover, correct processes deliver the same value. In other words, there is no disagreement in the reliable broadcast, which might not be the case when we consider implementing it in decentralized model. So we define the centralized trust model as a pair consisting of a quorum system map and a faulty scenario. Here, the map Q assigns a quorum system to each process, which represents its trust assumptions. We assume that a process includes itself in every quorum. While the individual quorum system represents what each participant expects from the system, the faulty model F indicates what failure scenarios might be manifested in the executions. Also, a correct process is called live in a fixed fault scenario if it has a quorum composed only by correct processes. So coming back to the simplified example, here, since Bob only trusts Alice, his only quorum is composed of Alice and himself, while Carl has multiple quorums. Now, if we use these trust assumptions to run a quorum-based protocol, we can see that if Alice is Byzantine, then the quorums of Carl and Bob will not intersect in a correct process. In order to capture this phenomenon, and also consider the case where the system might not always be consistent, we introduce a relaxed variant of broadcast protocol. We call this broadcast variant key-consistent broadcast, where we relax the consistency and termination guarantees of reliable broadcast, such that only live correct processes are guaranteed to deliver value from a correct source. Intuitively, we cannot guarantee progress to a process if every one of its quorums has a fault process that may become unresponsible during the execution. Moreover, up to k distinct values are delivered by correct process. In other words, we allow disagreement to occur, but it's limited by the parameter k. But how can we devise this parameter based on the trust assumptions? For this purpose, we use undirected graphs to represent trust assumptions. Given a specific fault scenario, F, and a single quorum for each correct process, the graph is built as follows. The nodes are correct processes and edges are drawn between two nodes if their selected quorums intersect in a correct process. Formally, we use a quorum map S, which assigns a quorum to each process and include an edge to a pair of processes if and only if the intersection of their assigned quorums is not a subset of F. For example, consider a system with 4 processes and a faulty scenario where only P3 may fail. If the quorums are assigned, such as the following, every pair of quorums for correct processes will intersect in P2, which is correct. The resulting graph is therefore fully connected. On the other hand, if we consider a quorum map such as S prime, the quorums assigned to P1 and P4 intersect only on P3. Thus, the resulting graph is missing an edge. Now, consider the family of graphs that includes a graph for every combination of fault scenarios and quorum maps. We use this family of graphs to define the inconsistency number of the trust assumptions. Formally, the inconsistency number of a pair composed of a quorum system map and a faulty model is the highest independence number among all the possible graphs generated over them. Recall that the independence number of a graph is the size of a maximum independent set, which in turn is a set of nodes, none of which is adjacent to another. Intuitively, an independent set in a graph spots vulnerabilities in the trust assumptions by grouping nodes that do not have their quorums intersecting in correct processes. We then show that no quorum-based algorithm can implement k-consistent broadcast with k less than the inconsistency number of the system, which is also shown to be tight. In our protocol, since the disagreement can prevent some correct processes from delivering a value, we introduce an accountability feature in order to achieve termination. This is called k-consistent reliable broadcast and provides the additional properties that a live correct process eventually terminates by either delivering a value or providing an irrefutable proof that the source is misbehaving. A source is accused only if it is faulty. Moreover, if a correct process accuses the source, that is, produces a proof of misbehavior, then eventually every correct process does so. The key idea behind the protocol is that every value is signed by the source, and the correct process echoes a received value to the entire network, so that if conflicting values are sent to correct processes, they are eventually discovered. As for the future work, we will explore which high-level abstractions can be implemented using a consistent, reliable broadcast. For instance, one might use the bounded disagreement to design a relaxed asset transfer system. Another interesting question is whether this analysis can be extended to weighted quorum systems, such as one based on the stake of each participant. Finally, the presence of disagreement and introduction of the accountability feature raises the important question of how we can use the information provided to the system application in order to automatically reconfigure the system. I thank you for your attention, and I hope this presentation has sparked your interest in the paper.